and welcome back to Miss Sogram's Maths. This is a worked solution video for the Level 3 Calculus External on Algebra and Complex Numbers, Achievement Standard 91577. Right, so question 1A, starting with an achieved question. There's a fair bit of achieved that can be done on the calculator, and I'll show you that as we go. Right, so we're told that WZ makes something, so that would be D plus 5i times 3 minus 4i makes 38 minus 9i. Now, if two things are times together, then if we can do a division, that makes things a bit easier. You could multiply out the brackets, but doing this division is a little more straightforward, especially when you have the calculator. So if we take 38 minus 9i, we need some brackets there as well. Let's just move it along. Okay, and we're going to divide by 3 minus 4i, and I'm getting that I just here using the shift. Then that will come to 6 plus 5i. So if we compare what we've got over on the left, d plus 5i is equal to 6 plus 5i, so d must be 6. Okay, z is equal to 2 plus 3i. We want to do 26 divided by z. So 26 over 2 plus 3i. Again, I'm not going to waste any time doing stuff by hand if we can do it on the calculator. So that is equal to 4 minus 6i. So we go along 4 in our real direction and minus 6 in the imaginary. So we have just here, this is 26 over z. All right, part C, we've got this polynomial. We've got some information about the remainder. Oh, let me just get that to fit. So it's got the same remainder when we divide it by minus 2 as it does when we divide it by plus 1 as those factors. Now we need to use that to work out the values of a and b. I'm going to use the remainder theorem here, which tells us that if we know what the remainder is, if we put the root that comes from the factor into our polynomial, then we will get that remainder. So the root that comes from x minus 2 is 2. So if we put that in, we will get 2 cubed plus 3 times 2 squared plus 2a plus b. From this other factor, we put in the root of minus 1. So minus 1 cubed is minus 1. And then we've got 3 times minus 1 squared, that's a plus 3. Then a minus a and a plus b. Now we're told that this is the remainder theorem, so this will equal the remainder, this will also equal the remainder, and we're told that those two remainders are the same, so we can set these two equations equal to each other. So this is 8, this here is 12, so add that up, we've got 20 plus 2a plus b is equal to this other one, so minus 1 plus 3 is 2 minus a plus b, and I'm going to go on and solve that. So I've got here that a is minus 6. I can't work out b at the moment because they would cancel each other out, but we do have this other bit of information up here that x plus 2 is a factor, which means the remainder would be 0. Or in other words, we can put in f of minus 2 from that factor and set it equal to 0. So if we put 2 into this equation, sorry, minus 2, it would be minus 8 plus 3 times 4, which would be 12. We know that a is minus 6, so minus 6 times minus 2 is 12, and then plus b, and that's going to equal 0. So then b is minus 16. Okay, part D, show that if we have this imaginary number 1 plus 3i, then the argument of doing this will give us pi by 4. Okay, so let's start off by doing this part and see what we get. So what I've done so far is substitute in the values for z and simplify. Now if we go over to our calculator, we can see what happens if we do this. So that division comes to 1.5 plus 1.5i. Now plot that onto an Argand diagram, and you can see it's going to make an isosceles triangle, so 1.5 on either side. So 1.5 in the real direction, 1.5i. So the argument here, so that will be equal to theta, which is equal to pi by 4. It's on that 45-degree line. You could maybe go a step further by saying that the real and imaginary parts are equal, but this will be sufficient. Right, the excellence part. We've got that the real part of this is 0. Z can't be 4. Don't worry about that too much. It's just saying that this can't be divided by 0. Prove the locus of the points described by Z will come to this. So the clue here is it's given you x and y's in this. So we want to turn this into that equation. Now this is called a Cartesian equation because it has the x's and y's in it. So what we first need to do is change the z's into the equivalent x's and y's that show the real and imaginary parts. So we've got that z is equal to x plus iy. So if we put that into this here, like so, we're going to carry on from there. And the first thing we do with it is to try to rationalize the denominator. So we're multiplying by the conjugate of the denominator. So that means we've taken this imaginary part of it and changed it into its opposite. So it's a negative on the imaginary stuff. The real stays the same. Multiplying that through will help us to get rid of any imaginary parts on our denominator. As you can see, what we're aiming for does not have any imaginary parts in it, so we start by getting rid of the ones in the denominator. Okay, so working through that algebra looks like this, which is pretty lengthy, but it's just going through and doing each of the terms times by each other on the top and the same on the bottom. Now go through and simplify. So, for example, we can get rid of that. They cancel each other out. And we end up with this one. If you want to pause and just see where I've got each bit, feel free. So now, if we are told that the real part of this is equal to 0, we can take a look at here and just take all of the real sections of it and equate it equal to 0. So that means that we will have the bit of the denominator will be equal to 0. I could have included the numerator is equal to 0. I could have included the denominator, but I would have ended up bringing it over and multiplying it by 0. So there's not really too much point. We can just look at the numerator for this one. And then carrying on solving through with that, I'm aiming to turn this into this type of equation. So what I've done with these bits is used completing the square on each of those. So turned that into a different format by using completing the square. And then you can see how it simplifies to be able to get that x minus 2 squared plus y minus 1 squared is equal to 5. All right, question 2a. Given that u is 2i and w is this other thing, find z where z is u over w. Okay, so before I get started on that, I've got one of them in polar form and one in Cartesian. So I'm going to change the u into polar form. Now just think about where that is on our Argand diagram. If it's 2i, it'll just be sitting right here on 2i, which means that it has a modulus of 2 and an argument of pi by 2, 90 degrees. So then u over w, we can use what we know about dividing in polar form, means that we will divide the moduluses of both of those things. So 2 divided by 2, because that's what we've got, modulus here, modulus there, and the arguments get subtracted. I'm not great at doing subtractions and additions of fractions, so I'm just going to use the calculator. So we get cis of negative pi by 6. Now we have what might look a little bit scary, but it's actually just a quadratic. And we're going to solve this quadratic. The only difference here is we've got q in there that we don't know what it is. So we're going to solve x in terms of q. You can do various different methods for this. We could do completing the square, but since I know most of you sort of default to using quadratic formula, I'm going to do that one. So we'll do x equals minus b. So minus b would be 12q. Plus or minus the square root of b squared, which is 144q squared. So just that bit there. Minus 4 times a, which is 1, times c, which is 20q squared, all over 2a, which is 2. Right, so we have 12q over 2, which is 6q, plus or minus the square root of, so this is going to be 144q squared minus 80q squared. So 144 minus 80 is 64. That's nice, comes to something we can square root. So this would be the square root of 64q squared over 2. So we've got 6q plus or minus, this would go to 8q, which then gets divided by 2. So that'll be 4q. So x equals, well, 6q plus 4q would be 10q, or 6q minus 4q would be 2q. Okay, part C, prove that this is purely imaginary. So we're going to try to simplify what we've got here. We'll start by timesing it through by the conjugate of the denominator, b plus ai. So we can rationalize that denominator. So I'll just pause and do the next bit. That's just multiplying through each term on the top and the bottom. So then we get ab plus a squared I plus b squared I. Then I squared becomes minus 1, so this is minus ab all over b squared minus a squared times the I squared makes it a minus 1, so then that becomes a plus a squared. Now here's the key part. ab there cancels with minus ab there, which means we get a squared plus b squared I over b squared plus a squared. So there's no real part. We've only got a bit that's got a coefficient of I, so therefore purely imaginary. And actually, even one step further, I just noticed that a squared plus b squared cancels 2, so it's actually just equal to I. Okay, for part D, we are solving this equation. Z cubed is equal to this complex number, and we need to work out Z. It's a cubic, so it means we will have 3 solutions here, and we're going to use de Moivre's theorem to find those 3 solutions. To use de Moivre's, we need this complex number written in polar form first, so let's figure out what that will be. So Z cubed, if we think about it on the Argand diagram, this k6 plus k6i, so we've got k6 along the real and along the imaginary axis. So we make this little triangle sort of situation. So if we want the modulus, we will need to square both sides, add them together, and then find the square root. So if I simplify that, it's 2 lots of k to the 12, and then find the square root of that, which would be the square root of 2, and then the square root of k12 is k6. So that's our modulus. So the root 2 k to the power of 6, and then we need the argument. So cis, and our argument here is just 45 degrees or pi by 4, because this is an isosceles triangle that we've got over here. Okay, now we can go ahead with the solving. So the first solution, the modulus gets cube rooted. So find the cubed root of root 2 and k to the 6. So root 2 would be 2 to the half, and then if we times that power of a half by a third to do the cubic root of it, this is what we get as 2 to the 6th. Then for the argument, we do the original argument of pi by 4, and we divide by 3, because we are solving that cubic, so the argument gets divided by 3. So this will become pi by 12. So a quarter divided by 3 is a 12th. Now for the second solution, what we're doing is imagining that this complex number that we started with, we could go a full way around the circle and back to here, and it would give us the same thing. So if it started as that, it would be, the modulus doesn't change. Oh, I just realized I left off the k part there on that first one. Okay, so the root 2 turns into 2 to the 6, and k to the 6, if we cube root that, is k to the 2, k squared. Okay, so moving back on with our second solution, we have the modulus stays the same as being 2 to the 6, k squared. Our argument, however, we start with our original pi by 4, we add on a full circle, so we can do that full turn around our Argand diagram again, and then divide it by 3. And that simplifies to 3 pi by 4. You can do it on your calculator using the fractions if you're not so confident with that. Just put in a quarter plus 2 and then divide the whole lot by 3. Okay, final solution, the third one. Again, the modulus will be the same, but the argument now will be, instead of going around once, we'll go around twice and then back to here. So that'll give us pi by 4 as the first one, but then plus 4 pi because we're adding 2 more around the circle, like so. And that simplifies to an argument of 17 pi by 12. Now, one small thing to notice, not a major if, you can leave it like this and it would still be accepted, but when we go around past that 180 line, which is pi. So if we get a top heavy fraction, hold on this bit just here, then we prefer to write that as if we were going this direction under the axis to the same point instead. That's where we think about principal argument. So if we were going in the opposite direction, that would be equivalent to it being minus 7 pi by 12. So we just take 17 over 12, subtract it from 2, and we've got minus 7 over 12. Okay, part E for excellence. We have z as a complex number, and there's this relationship going on with z. We'll need to work on modulus. That's what these straight lines mean. So we will express z in terms of x plus iy, and we know when we've got it that way round, we can work out the modulus of z is x squared plus y squared. So then taking this bit that we have here and replacing z with x plus iy, we will get these. So the z plus 16 becomes this, and then on the right hand side we get this. Now taking the modulus of the left hand side means that we will take the real part and square it, and then the imaginary coefficient and square it, and find the square root of that, and then do the same on the right. So on the left, if we sort that out, we get that expands to this. So I've just expanded the bracket. Haven't taken the square root in this one because what I've done is squared both sides as well. So make that into a 16, and then we can remove the square root sign and expand the brackets of what's inside. So this on the right then looks like that. And we end up with, working that through, we get 15x squared plus 15y squared is equal to 240. If we divide through by the 15, we'll get x squared plus y squared is equal to 16. Now remember, x squared plus y squared, I just realized I missed a square root up at the top there. Modulus is the square root of those things. So using x squared and y squared, that gives us modulus. So to turn that into the modulus, we would take the square roots there. So the modulus of z will be equal to 4. Right, 3a, we've got this complex number like this. The modulus is equal to 6. The argument is between 0 and pi by 2, which tells us it's in the first quadrant. So we have where this is 5, and this would be m. So we've got this rectangle M and 5. So m squared plus 5 squared will be equal to 6 squared because we're told that modulus is 6. And working that through, we get that m is the square root of 11. For part B, we are going to rationalize the denominator so that we can, oh, that should be a 3, so that we can get rid of the square roots on the bottom. So we use the denominator but with a plus instead of a minus on the square root portion of it. Now I'm going to multiply those through. I realised I've made a mistake. That wasn't 24, so 2 root 3 times 2 root 3 would be 4 times by 3, so that's just 12. Okay, so 16 minus 12 is 4. So 72 divided by 4, 18 plus 9 root 3. Okay, part C. One solution to this is that z is 2 plus 5i. We know that a is a real number. We want to find the value of it, and then the other two solutions of this equation. Right, so if our first solution is 2 plus 5i, straight away your second solution is 2 minus 5i because complex conjugates are always roots in pairs like this. And then we just need to find the third one. I think since we have the calculator there, I'll go for working out a first. So if we put 2 plus 5i into our calculator, and I'm going to do 4 times that cubed minus 19 times it squared plus 128 of it is going to be equal to 87. So sub in z1 and we get that 87 plus a is equal to 0, so a is equal to minus 87. Okay, next we have if 2 plus 5i is a root, then z minus 2 plus 5i is a factor, and also z minus 2 minus 5i from this one is also a factor. So we can multiply that together. So that one will cancel with that one, that with that. We will get z squared minus 4z plus 4. Then this I squared here is minus 1, so it makes it into a plus 25. So that'll be a plus 29. All right, now compare that to the original, because we are looking for the third factor. That's minus 87. So that will equal to z squared minus 4z plus 29 times by az plus b. Okay, so to make 4z cubed, we need z squared times az. So a must be 4. To make 87, we need, let's go, 87 divided by 29 is 3. So b must be minus 3. So the other factor, so 4z minus 3 is a factor. So our third solution, z3, will be 3/4. Right, part D, solving for x in terms of m. Let's start by squaring both sides. So we will have 6 root 2x minus 5 times 6 root 2x minus 5. And I'm writing the whole thing out in full to make sure that we don't miss anything, because it's easy to miss pieces on this. So that right-hand side, if we square that, we will end up with 36 times by this. Then our next line looks like this. And then I'm going to go through, do a bit more tidying up. Now that 72 cancels with that one. Okay, so we get minus 60 root 2x is equal to 36m minus 25. So root 2x will be equal to, it'll be 25 minus 36m because I've taken the negative into account from here. That negative, if I bring it over, we'll just switch those two over. 5 degrees because our x direction and y direction will be the same length. Comparing the imaginary side of this equation, on the left we have 2xy, and on the right we have all of this bit. So we work that through. We've just found that x squared and y squared are the same, so we can replace the y squared with x squared here. So 2xy is equal to 2x squared minus 4. Now think about this on an argand diagram. If we're saying that x squared is equal to y squared, then it means either that x is equal to y, which would give us these two possibilities, or that x is equal to minus y. So solving this here with the square roots involved, it could be x is y or x is equal to minus y. So we've got some possibilities to think through here. So if x was equal to y, then we would have that 2x squared is equal to 2x squared minus 4 by putting x equals y into this equation here. Now that can't be true. Those two things don't match up, so that gives us an invalid solution. So x is not equal to y. So it's got to be that x is equal to minus y. So let's just check that. If we pop that into here, we get minus 2x squared is equal to 2x squared minus 4. We can work that through. So we get 4x squared is equal to 4. Therefore, working that through, x could be 1, in which case we would get y is equal to minus 1, since x is equal to minus y. We could also get that x is minus 1 from solving this, in which case y would be 1. So then we have, just one sec. There are two possible solutions. So z being x plus iy, if x was 1, then the y was minus 1, so that gives us 1 minus I. And if x is minus 1, y is plus 1, so that gives us minus 1 plus I by substituting it back into that z equals x plus iy.